In 1996, a woman named Elizabeth Everett killed herself. She was 39 years old. She had struggled with mental illness for most of her adult life, and in the end, she made a decision that her family had seen coming for years. But her suicide note contained something that nobody expected: instructions for her remains. She wrote that she wanted to be cremated, and she did not want her ashes kept. She wanted them thrown in the garbage. And then she explained why. She wrote that if her ashes were disposed of this way, she might end up in the correct parallel universe to meet up with Daddy. Her father was Hugh Everett III. He had died 14 years earlier, in 1982, of a heart attack at the age of 51. He was an alcoholic. He was grossly overweight. He never exercised. He had asked for the same thing Elizabeth asked for: throw my remains in the trash. His wife kept his ashes in a filing cabinet for a few years, then complied with his wishes. Now his daughter wanted the same. She believed, apparently, that disposing of her ashes this way would help her reach him in another universe, a parallel world, a branch of reality where things had gone differently. This might sound like the magical thinking of a person in crisis, but Elizabeth Everett was not inventing this idea. She was referencing her father's work. Hugh Everett III was a physicist. In 1957, he published a paper that proposed something so radical that the physics establishment refused to engage with it. He proposed that every time a quantum measurement occurs, the universe does not collapse into a single outcome. It branches. Both outcomes happen. Both are real. And this branching happens constantly at every quantum event throughout the entire universe, forever. The theory is called the many worlds interpretation of quantum mechanics. You have probably heard of it. You have probably seen it explained on other channels, in other videos, in books and podcasts and documentaries. You probably think you understand what it means. Parallel universes where different versions of you made different choices. Somewhere out there, a version of you asked out your high school crush. A version of you took that other job. A version of you is a rock star, or a failure, or dead or alive, or anything else you can imagine. That is not what the theory actually says. Or rather, that is a small and sanitized piece of what the theory says. The part that sounds whimsical. The part that sounds like science fiction. The part that physicists are comfortable putting in popular books and YouTube videos. What the theory actually implies, when you follow the mathematics to its conclusion, is something else entirely. Something that the physicists who accept this interpretation have largely declined to discuss in public. Something that, if true, means you are not who you think you are. You are not a continuous entity moving through time. You are not a single person who will wake up tomorrow as yourself. You are something else. Something that is created and destroyed billions of times per second. Something that exists for an instant and is then annihilated, replaced by copies who remember being you but are not you. And if this sounds disturbing, it should. Because the many worlds interpretation is not fringe physics. It is not a thought experiment that physicists entertain for fun. It is the second most popular interpretation of quantum mechanics among working physicists. When you survey people who actually work on quantum foundations, roughly 15 to 20% of them say they think many worlds is probably correct. Some of the most prominent physicists of the last 50 years have endorsed it. Stephen Hawking once said he regarded it as self-evidently correct. Sean Carroll wrote an entire book arguing that it is probably the right way to understand reality. David Deutsch, one of the pioneers of quantum computing, considers it obviously true. These are not cranks. These are not fringe figures. These are mainstream respected physicists at major institutions. And they are telling you that reality is constantly branching into countless copies of itself, that you are splitting into multiple versions every moment, and that this process has been happening since the beginning of the universe and will continue until its end. And here is the part that should make you angry. Here is the part that almost nobody talks about. If these physicists are right, if the many worlds interpretation is the correct description of reality, then it has profound and horrifying implications for your existence as a person, for your identity, for your continuity through time, for the meaning of your choices and the nature of your suffering. These implications follow directly from the mathematics. They are not speculative. They are not philosophical hand-wringing. They are logical consequences of the theory. And the physicists who accept this theory, who consider it probably true, who write books and give lectures defending it, have by and large chosen not to discuss these implications. They mention them briefly and move on. They acknowledge them in footnotes. They gesture at them and then change the subject. They treat the implications as a distraction from the real physics, as if the question of what happens to you when reality branches is less important than the equations that describe the branching. This video is about those implications, the ones that nobody was supposed to find, the ones that follow from the mathematics that physicists have been working with for nearly 70 years. The conclusion about you that the many worlds interpretation actually contains, hiding in plain sight, waiting for someone to say it out loud. But to understand what that conclusion is, we first have to understand why physicists were backed into this corner in the first place. We have to understand the problem that many worlds was invented to solve, and we have to understand why, after almost a century of trying, nobody has found a better solution. Quantum mechanics is the most successful scientific theory in human history. That is not an exaggeration. It is not hyperbole. The predictions of quantum mechanics have been verified to more decimal places than any other physical theory ever constructed. When physicists calculate the magnetic moment of the electron using quantum electrodynamics, their prediction matches experimental measurements to better than 10 parts in a billion. That is like predicting the distance from New York to Los Angeles and being accurate to within the thickness of a human hair. The technology you are using to watch this video exists because quantum mechanics works. Transistors work because quantum mechanics is correct. Lasers work because quantum mechanics is correct. MRI machines work because quantum mechanics is correct. Every piece of modern electronics, every computer chip, every LED screen, every solar panel is a testament to the stunning accuracy of quantum mechanical predictions. And yet, after nearly 100 years, physicists cannot agree on what quantum mechanics actually means. They can use it to calculate. They can use it to predict. They can use it to build technologies that would look like magic to anyone from the 19th century. But when you ask them what is actually happening, when you ask them what the equations are describing, when you ask them what reality is actually doing when a quantum measurement takes place, they start to disagree. Violently, fundamentally, in ways that have never been resolved. This is the measurement problem, and it is, by some measures, the most embarrassing unsolved problem in the foundations of physics. Here is the issue in its simplest form. Quantum mechanics describes particles using something called a wave function. The wave function is a mathematical object that contains all the information about a quantum system. Before you measure a particle, the wave function can describe the particle as being in a superposition of states. This is not a metaphor. This is not a way of saying that we do not know which state the particle is in. The mathematics of quantum mechanics explicitly describes the particle as being in multiple states simultaneously. An electron can be spin up and spin down at the same time. A photon can travel through both slits of a double-slit apparatus at the same time. These superpositions are real, in the sense that they produce measurable interference effects that could not occur if the particle was secretly in just one state all along. But when you measure the particle, something strange happens. You never observe a superposition. You always observe a definite outcome. The electron is spin up or spin down. The photon went through the left slit or the right slit. The superposition seems to vanish the moment you look at it. The standard story, the one you learn in physics classes, is that measurement causes the wave function to collapse. The superposition is destroyed. The particle chooses one outcome with probabilities given by the Born rule, and that outcome becomes reality. This is called the Copenhagen interpretation, named after the city where Niels Bohr developed it in the 1920s and 30s. But here is the problem: nobody has ever explained what collapse actually is. Nobody has ever identified a physical mechanism that causes it to happen. Nobody has ever been able to write down the equations that govern when it occurs or why. Collapse is not a prediction of quantum mechanics. It is something that was added to the theory by hand to make the mathematics match our observations. Think about what that means. We have the most successful predictive theory in the history of science, and at its heart, where it describes the interaction between quantum systems and measurements, there is a gap, a placeholder, a thing that we do not actually understand. We just say collapse happens and move on. And it gets worse, because the Copenhagen interpretation does not just fail to explain collapse, it relies on a concept that it cannot define. It relies on the concept of measurement, of observation, of looking at the system, but what counts as a measurement? What makes something an observer? You might think the answer is obvious. A measurement is when a physicist looks at the result. An observer is a conscious being who perceives the outcome. But this answer creates enormous problems. Consider this. You have a particle in a superposition. A detector measures it. According to Copenhagen, the wave function should collapse when the detector measures the particle. But wait, the detector is made of atoms. The atoms are quantum systems. Why does the detector not enter a superposition along with the particle? Why does the detector collapse the wave function instead of becoming entangled with it? You might say the collapse happens when the detector records the result. But recording is just a physical process. The detector's atoms move, electrons flow, a display changes state. All of these are quantum mechanical processes. There is nothing in the equations that says a detector should cause collapse while a particle should not. So maybe the collapse happens when a human looks at the detector. But human eyes are made of atoms too. Human brains are made of atoms. If you follow the Copenhagen logic, you end up saying that the superposition propagates through the detector, through the air, into the human eye, through the optic nerve, into the visual cortex, and then collapses at some point when the human becomes consciously aware of the result. This is called the von Neumann chain, named after the mathematician who first described it, and it leads to an absurd conclusion. It seems to say that consciousness causes collapse. That reality is observer-dependent in some deep and mysterious way, that the human mind plays a special role in the foundations of physics. Some physicists have embraced this conclusion. Eugene Wigner, one of the greatest physicists of the 20th century, seriously entertained the idea that consciousness might be necessary to collapse the wave function. But most physicists find this deeply unsatisfying. It seems to make physics dependent on philosophy of mind. It seems to give humans a privileged position in the universe that nothing else justifies. And it still does not actually explain what collapse is, or how it works. Erwin Schrodinger, one of the founders of quantum mechanics, knew this was a problem. That is why he invented the thought experiment that bears his name. You know the setup. A cat in a box with a radioactive atom, a detector, and a vial of poison. If the atom decays, the detector triggers the poison and the cat dies. If the atom does not decay, the cat lives. According to quantum mechanics, before anyone opens the box, the atom is in a superposition of decayed and not decayed. And if superpositions propagate through physical systems the way the equations say they should, then the cat should also be in a superposition, alive and dead at the same time. Schrodinger did not invent this thought experiment to celebrate quantum mechanics. He invented it to attack the Copenhagen interpretation. He was saying, Look how absurd your theory is. Look where it leads if you take it seriously. You end up with cats that are alive and dead simultaneously. Clearly something is wrong. But here is the thing. The physics community heard Schrödinger's critique and then did something strange. They basically shrugged. They said, yes, the cat is in a superposition, but it collapses when you open the box. They said the cat is both alive and dead until someone looks. They turned Schrödinger's reductio ad absurdum into a feature of the theory. They put it on t-shirts. And for decades, that was considered good enough. The equations worked. The predictions matched experiments. Nobody could figure out what measurement actually was, or when collapse actually happened. But so what? Shut up and calculate. That phrase became the unofficial motto of quantum mechanics. Do not ask what the equations mean. Just use them to make predictions. Philosophy is for philosophers. This attitude was enforced, actively enforced. Graduate students who asked too many questions about the foundations of quantum mechanics were warned that it was not a good career move. Jobs were at stake. Reputations were at stake. The culture of physics in the mid-20th century was actively hostile to anyone who took the measurement problem too seriously. John Clauser, who would later win the Nobel Prize for testing Bell's theorem, described the atmosphere as dogmatic. He said that physicists who questioned the Copenhagen interpretation were treated as fools or heretics. He said that when prominent figures like Einstein and Schrödinger continued to express discomfort with the theory, they were dismissed by professional gossip as having become senile. The message was clear: accept the standard interpretation. Do not ask difficult questions. Move on. And so for decades, the measurement problem sat there, unsolved, unaddressed, an embarrassment at the heart of the most successful scientific theory ever constructed. Physicists could calculate the magnetic moment of the electron to 11 decimal places, but they could not explain what happens when you measure it. They could build technologies that reshaped the world, but they could not say what reality is actually doing when a quantum event takes place. This was the landscape in 1954, when a 23-year-old graduate student at Princeton sat down with some colleagues after a few glasses of sherry and started thinking up ridiculous things about the implications of quantum mechanics. His name was Hugh Everett III. He had arrived at Princeton on a National Science Foundation fellowship, originally to study mathematics. He had drifted into physics almost by accident, taking his first quantum mechanics course with Robert Dicke in 1953. He was brilliant in a broad, unfocused way. His roommate, Harvey Arnold, said he was smart enough to go from chemical engineering to mathematics to physics, while spending most of his time buried in science fiction books. He had written to Albert Einstein when he was 12 years old, asking about the irresistible force and the immovable object. Einstein had written back, calling him a stubborn boy who had forced his way through strange difficulties of his own creation. Now Everett was at Princeton, working with John Archibald Wheeler, one of the most influential physicists of the 20th century. Wheeler was the kind of physicist who asked big questions. He coined terms like black hole and wormhole. He pushed his students to think beyond the conventional wisdom. And Everett was exactly the kind of student who was willing to push. That evening in 1954, Everett was drinking with Charles Missner, a fellow graduate student, and A.J. Peterson, a visiting physicist who worked as Niels Bohr's assistant. They were talking about quantum mechanics, about the absurdities of the Copenhagen interpretation, about the measurement problem and the infinite regress and the question that nobody seemed able to answer. And somewhere in that conversation, fueled by sherry and frustration and the freedom that comes from late nights among friends, Everett saw something. A way out of the trap. A solution so simple and so radical that nobody had been willing to consider it seriously. What if collapse never happens? What if the wave function never reduces to a single outcome? What if it just keeps evolving, smoothly and continuously, according to the Schrodinger equation, forever. The mathematics of quantum mechanics already described what would happen. If you have a particle in a superposition and it interacts with a detector, and the detector does not collapse the superposition, then the detector enters a superposition too. The detector becomes entangled with the particle. If the particle was spin up and spin down, now the detector is in a superposition of having measured spin up and having measured spin down. And if a human looks at the detector and the human does not collapse the superposition, then the human enters a superposition too. One version of the human sees spin up, another version sees spin down. Both versions are real. Both versions exist. Both versions continue on, each convinced that the measurement had a single definite outcome, neither aware of the other. This was Everett's insight. The wave function does not collapse. It never collapsed. What looks like collapse from the inside is actually branching. The universe splits. Every quantum outcome that the mathematics says is possible actually occurs. We only perceive one outcome because we are inside one branch. The other outcomes are real too. They are just in branches we cannot access. This solves the measurement problem in one stroke. There is no collapse. There is no special role for observers. There is no need to define what counts as a measurement. Everything is quantum. Everything evolves according to the Schrodinger equation. The apparent specialness of measurement is an illusion created by our position inside the branching structure. Everett spent the next 2 years developing this idea into a complete mathematical framework. He called it the theory of the universal wave function. He showed how the branching process emerges naturally from the standard equations of quantum mechanics. He showed how observers inside a branch would perceive random outcomes even though the underlying evolution is deterministic. He showed how the probabilities predicted by the Born rule could be understood as a natural consequence of the branching structure. His thesis advisor, John Wheeler, was initially enthusiastic. Here was a young physicist who had potentially solved the most vexing problem in quantum foundations. Wheeler helped Everett refine the mathematics. He encouraged him to develop the implications. He thought this might be the breakthrough the field had been waiting for. But Wheeler was also nervous, because he knew that Everett's theory would not be received well in Copenhagen. He knew that Niels Bohr, the patriarch of quantum mechanics, would not accept the idea that his interpretation was wrong. He knew that challenging Copenhagen meant challenging the establishment, and the establishment had ways of destroying careers. So Wheeler started pressuring Everett to soften the thesis, to remove the provocative language, to take out the passages where Everett directly attacked the Copenhagen interpretation. The original thesis was about 137 pages. By the time Wheeler was done with it, the published version was barely half that length. An entire chapter had been removed, including a vivid analogy where Everett compared branching observers to dividing amoebas. Wheeler had scribbled in the margin of that passage, asking for better words than split. The watered-down version was published in the Reviews of Modern Physics in July of 1957. Wheeler had given it a new title, Relative State Formulation of Quantum Mechanics, which sounded much less threatening than Everett's original approach. Wheeler also contributed a companion paper praising Everett's work while carefully noting that it was consistent with the Copenhagen interpretation if viewed in the right way. It was a compromise, and like most compromises, it satisfied nobody. Wheeler had arranged for Everett to visit Copenhagen in 1959 to present his ideas directly to Bohr. Everett traveled with his wife Nancy and their infant daughter Elizabeth. The trip was a disaster. Everett later described it as hell, doomed from the beginning. He spent 6 weeks in Copenhagen trying to explain his theory to physicists who had no interest in understanding it. Leon Rosenfeld, one of Bohr's closest collaborators, later wrote about the visit with undisguised contempt. He said that neither he nor Bohr could have any patience with Everett. He called Everett's ideas hopelessly wrong. He said Everett was, In his words, undescribably stupid and could not understand the simplest things in quantum mechanics. This was not a substantive critique. This was an establishment closing ranks against a threat. Everett had challenged the Copenhagen interpretation, and the Copenhagen interpretation had responded by declaring him a fool. The 1957 paper, published to complete silence, slipped into instant obscurity. It received almost no citations for over a decade. The physics community had rendered its verdict. Everett was wrong. The measurement problem was solved, or at least did not need to be solved. Shut up and calculate. Everett left physics. He had already taken a job at the Pentagon before finishing his thesis, partly because he needed money, and partly because he saw no future for himself in academia. He joined the Weapons Systems Evaluation Group working on nuclear strategy for the Department of Defense. He calculated fallout patterns from nuclear weapons. He helped develop theories of mutually assured destruction. He advised presidents on how to manage the end of the world. He never returned to theoretical physics. In 1977, when he presented his ideas at a conference for the first time in 20 years, he told the audience that he had washed his hands of the whole affair in 1956. He sounded bitter. He was bitter. He had proposed a solution to the central problem in quantum foundations, and the physics establishment had ignored him for 2 decades. His advisor, John Wheeler, eventually abandoned him too. At the Einstein Centenary Symposium in 1979, Wheeler publicly withdrew his support for Everett's interpretation. He said he had reluctantly given up on it because it carried too much metaphysical baggage. This was exactly the kind of criticism that the Copenhagen interpretation was vulnerable to, but Wheeler did not seem to notice the irony. Years later, Wheeler expressed regret. At 95 years old, he said he wished he had kept up the sessions with Everett. He acknowledged that Everett had been disappointed, perhaps bitter, at the non-reaction to his theory. But by then, it was too late. Everett was dead. Hugh Everett died on the night of July 18th through 19th, 1982. He was 51 years old. His heart gave out while he was sleeping, fully clothed, on top of his bed. He was legally drunk at the time of death. His son Mark, who was 18, found the body the next morning. Mark later said that touching his father's corpse was the first physical contact between them that he could remember. Hugh Everett had been a ghost in his own family. Mark described him as a lump of furniture sitting at the dining room table with a cigarette in his hand. He said his father was in his own parallel universe. He said his father never told him anything about his theories. The man who had proposed that reality constantly branches into parallel versions of itself had become unreachable to the people who shared his home. The man who had argued that every possible outcome occurs had retreated into a single narrow track of alcoholism and isolation and slow self-destruction. And if his theory was correct, then somewhere in the branching structure of reality, there are versions of Hugh Everett who made different choices. Versions who stayed in physics, versions who saw their theory accepted, versions who watched their daughter grow up healthy and happy, versions who held their grandchildren, versions who are still alive right now in some branch we cannot reach, wondering what their lives might have been like if things had gone differently. But those branches are not accessible to us. The Hugh Everett we got, the one in this branch, drank himself to death in his bed at 51, and his daughter, 14 years later, killed herself at 39, asking for her ashes to be thrown in the garbage so she might reach him. If many worlds is true, Elizabeth Everett was right. There are branches where her father is alive. There are branches where she is alive with him. There are branches where everything went differently for the Everett family, where the theory was accepted and the physicist was celebrated, and the children grew up knowing their father. But we cannot reach those branches, and neither could she. The theory that should have made Hugh Everett famous was buried for decades. The establishment that should have engaged with his ideas dismissed them without serious consideration. The physics community that should have recognized his contribution treated him as a crank or a fool. And by the time the world caught up to what he had proposed, he was dead, his family was shattered, and the question at the heart of his theory, the question of what happens to you when reality branches, remained unanswered. But the theory did not stay buried forever, because in 1968, a physicist named Bryce DeWitt learned something that astonished him. He learned that there was a paper in the very journal he read regularly, published over a decade earlier, proposing a complete solution to the measurement problem, and he had never heard of it. Nobody had heard of it. It had been completely ignored. DeWitt decided to fix that. Bryce DeWitt was a theoretical physicist at the University of Texas, known for his work on quantum gravity and the structure of space-time. In the summer of 1968, he was visited by Max Jammer, a historian of physics who was writing a book about the interpretation of quantum mechanics. In the course of their conversation, DeWitt mentioned Hugh Everett's work on the relative state formulation. Jammer had never heard of it. DeWitt was stunned. Everett's paper had been published in the same issue of Reviews of Modern Physics that contained contributions from a gravity conference DeWitt himself had organized. The paper had been sitting there, in a journal DeWitt read regularly, for over a decade, and nobody knew about it. The physics community had simply looked past it. The most radical solution to the measurement problem ever proposed had been completely ignored. DeWitt obtained a copy of Everett's original uncut thesis, the one that Wheeler had made him shorten, and read it carefully. He was initially skeptical. When he first considered the idea that the universe branches every time a quantum measurement occurs, his gut reaction was to reject it. He wrote to Everett with what he thought was a devastating objection. He said that he simply could not accept a theory that implied reality splits, because we never feel ourselves branch. We never perceive the splitting. If it were happening constantly, surely we would notice something. Everett's response became legendary. He wrote back to DeWitt with a simple question. I cannot resist asking, do you feel the motion of the Earth? DeWitt had to admit that he did not. The Earth is spinning at over 1,000 miles per hour at the equator. It is orbiting the Sun at nearly 70,000 miles per hour. It is hurtling through the galaxy at hundreds of thousands of miles per hour. And we feel none of it. We had no idea any of this motion was happening until scientists worked it out from indirect evidence. If we can be completely unaware of the Earth's motion, why should we expect to feel the branching of reality? It was, DeWitt later admitted, a pretty good response. Everett was comparing his theory to Copernicus. Just as Copernicus had shown that our intuitive sense of a stationary Earth was wrong, Everett was showing that our intuitive sense of a single unbranching reality was wrong. Both required accepting that our perceptions do not directly reveal the true structure of the world. DeWitt reversed his position. He became the most devoted champion of Everett's ideas in the physics community. In September of 1970, he published an article in Physics Today titled Quantum Mechanics and Reality. This article coined the term that would stick. DeWitt called it the many worlds interpretation. The article was provocative by design. DeWitt wrote that every quantum transition taking place in every star, in every galaxy, in every remote corner of the universe is splitting our local world on Earth into myriad copies of itself. He made the implications vivid and inescapable. He forced readers to confront what Everett's mathematics actually meant. The response was enormous. Physics Today received more letters about DeWitt's article than about almost anything else they had published. The physics community was finally paying attention. Some were hostile, many were confused, but nobody could ignore it anymore. In 1973, DeWitt and his colleague Neil Graham published an anthology called The Many Worlds Interpretation of Quantum Mechanics. Crucially, This book included Everett's original long thesis for the first time. The material that Wheeler had forced him to cut was finally available to the physics community. The book sold out completely. The timing was right. By the early 1970s, a new generation of physicists had entered the field. They had not been trained under the shadow of Bohr. They had not absorbed the message that questioning the Copenhagen interpretation was career suicide. They were willing to take foundational questions seriously. And Everett's approach, preserved and promoted by DeWitt, found a receptive audience. Among that audience was a young physicist named David Deutsch. In 1977, when Hugh Everett finally presented his ideas at a conference at the University of Texas, Deutsch was in the audience. He was a graduate student of John Wheeler's, the same Wheeler who had been Everett's advisor 2 decades earlier. Deutsch watched Everett present in his rumpled black suit, chain-smoking through the session, and he was converted. Deutsch would go on to become one of the most important physicists of the late 20th century. He is considered one of the founding figures of quantum computing, and his work on quantum computation was in part motivated by the many worlds interpretation. The way Deutsch saw it, quantum computers were proof that Everett was right. Here is the argument. A quantum computer does not just process information the way a classical computer does. It exploits superposition and entanglement to perform computations that would be impossible for any classical machine. When you run a quantum algorithm like Shor's algorithm for factoring large numbers, the quantum computer does not check each possible factor one at a time. It somehow evaluates all the possibilities simultaneously. But where is this computation happening? A quantum computer with 300 qubits operates in a state space larger than the number of atoms in the observable universe. No classical description could capture all the possible states, and yet the computation succeeds. The answer emerges: the resources that the quantum computer is using vastly exceed anything available in our observable universe. Deutsch's answer is that the computation is happening across parallel universes. The different branches of the quantum superposition are performing different parts of the calculation, and then the results are combined through interference. When Google announced in 2024 that their quantum chip Willow had solved a problem in under 5 minutes that would take classical supercomputers 10 septillion years, Google's director Hartmut Neven said it lent credence to the notion that quantum computation occurs in many parallel universes. This is not proof. The many worlds interpretation makes the same empirical predictions as the Copenhagen interpretation for all feasible experiments. You cannot design a test that would distinguish them. But Deutsch argues that if you reject many worlds, you have to explain where the computational resources are coming from. You have to explain how a quantum computer can do what it does without the parallel branches. And this brings us to the argument that has converted many physicists to the many worlds side. The argument that turns the intuitive objection on its head, because the common reaction to many worlds is to say it is extravagant, it is unparsimonious, it postulates an infinite number of parallel universes when the Copenhagen interpretation gets by with just one. Surely the simpler theory is better. But this objection misunderstands what the many worlds interpretation actually says. It misunderstands where the many worlds come from. The many worlds interpretation does not add anything to quantum mechanics. It does not postulate extra universes. It does not introduce new equations or new physical mechanisms. All it does is take the existing mathematics of quantum mechanics seriously. It says that the wave function, the mathematical object at the heart of quantum mechanics, is real. It describes reality, and it never collapses. The potential for multiple worlds is not something that many worlds adds to quantum mechanics. The potential is already there in the wave function, in the Schrodinger equation, in the mathematics that everyone agrees on. The superpositions are there whether you like them or not. The entanglements are there whether you acknowledge them or not. When you measure a particle in a superposition, the mathematics says you become entangled with it. Both outcomes occur. Both branches are real. What the Copenhagen interpretation does is add something to the mathematics. It adds collapse. It adds a mechanism that is never specified, triggered by conditions that are never defined, that destroys all the branches except one. This collapse is not in the Schrodinger equation. It is not derived from first principles. It is stuck on by hand to make the mathematics match our intuitions about a single reality. Carroll puts it this way in his book, Something Deeply Hidden. He says that many worlds does not assume a large number of worlds. What it assumes is a wave function evolving according to the Schrodinger equation. The worlds are there automatically. To get rid of the other worlds, you have to add something to the theory. You have to add collapse, and collapse has no empirical support whatsoever. This is why Carroll, Deutsch, Tegmark, and others argue that many worlds is actually the simplest interpretation. It is the one that takes the mathematics at face value. It is the one that does not add epicycles to save our intuitive prejudices about a single branching reality. The counter-argument, of course, is that simplicity should be measured by the number of entities you postulate, not the number of laws. And many worlds postulates infinitely many entities, but proponents respond that an entire ensemble of worlds described by a single wave function is simpler, in the sense of Kolmogorov complexity, than a single world governed by laws that include an unexplained collapse mechanism. The debate has not been settled. But something shifted in the 1980s and 1990s that made the many worlds position much harder to dismiss. That something was decoherence. Decoherence is a physical process that was first described by H. Dieter Zerr in 1970 and developed extensively by Wojciech Zurek and others in the following decades. It explains why we never see macroscopic superpositions in everyday life. It explains why cats are not both alive and dead, and it does so without invoking collapse. Here is how it works. When a quantum system interacts with its environment, it becomes entangled with that environment. An electron in a superposition interacts with air molecules, photons, stray electromagnetic fields, all the things that surround it. Each component of the superposition interacts differently with the environment. Spin up pushes the air molecules one way, spin down pushes them another way. The electron becomes entangled with billions of environmental particles. This entanglement has a crucial consequence. It destroys the interference between the branches. In a pristine superposition, the different components can interfere with each other. That interference is what produces the characteristic quantum effects in experiments like the double slit. But once the system is entangled with the environment, the interference effects become unobservable. They are still there in principle, but they are spread across so many environmental particles that no feasible experiment could detect them. The result is that the different branches effectively become separate worlds. The branch where the electron is spin up and the branch where it is spin down can no longer interact or interfere. From the perspective of anyone inside either branch, it looks like a single definite outcome occurred. It looks like collapse happened, but no collapse actually took place. The wave function just became entangled with the environment in a way that made the different branches independent. This is exactly what the many worlds interpretation says should happen. Decoherence provides the mechanism. It explains why the branches become effectively separate. It explains why observers in each branch perceive a single outcome. It explains why the universe appears classical at macroscopic scales, even though the underlying physics is quantum mechanical. Zerr, who discovered decoherence, always regarded it as naturally leading to an Everettian picture of reality. The branches are real. They become separate through entanglement with the environment. The appearance of collapse is an illusion generated by our position inside one branch. Not everyone agrees that decoherence solves the interpretation problem. Critics point out that decoherence explains why we do not see interference between branches, but it does not explain why we see definite outcomes in the first place. It explains how the branches become separate, but not why we find ourselves in one branch rather than another. This is related to the probability problem in many worlds, which remains controversial. But decoherence has fundamentally changed the terms of the debate. Before decoherence was understood, the many worlds interpretation seemed to face an insurmountable problem. How could the branches separate? Why would we not observe interference between them? Decoherence answered those questions. It showed that the branching is not just a mathematical abstraction, it is a physical process that happens whether we interpret the mathematics as many worlds or not. The wave function really does branch. The different outcomes really do become independent. The only question is whether the other branches are real, or whether something we cannot explain causes them to disappear. And here is where the many worlds interpretation becomes personal. Here is where the mathematics starts to have implications for you. Because if the branches are real, if every quantum outcome occurs, if you are splitting into multiple copies every time a quantum event occurs in your brain, then we have to ask a question that physicists have largely avoided. What happens to you when the universe branches? This is not a question about physics. The physics is settled. The Schrodinger equation tells you what happens to the wave function. Decoherence tells you how the branches separate. The mathematics describes the process completely. What the mathematics does not tell you is which branch you end up in, or whether there even is a you that ends up anywhere. Consider a simple case. You measure the spin of an electron. Before the measurement, the electron is in a superposition of spin up and spin down. After the measurement, according to the many worlds interpretation, there are two branches. In one branch, the electron is spin up and you observe spin up. In the other branch, the electron is spin down and you observe spin down. Both branches are real. Both versions of you are real. Both of them remember being you before the measurement. Both of them have complete psychological continuity with the person you were a moment ago. They share all your memories, all your personality traits, all your beliefs and desires and hopes and fears. So which one is you? The intuitive answer is that you are one of them, and the other one is a copy. Maybe the one who measured spin up is really you, and the one who measured spin down is a newly created duplicate. Or maybe it is the other way around. Either way, there is a fact of the matter about which branch is yours. But the mathematics does not support this answer. The mathematics treats both branches identically. There is nothing in the wave function that marks one branch as the original and the other as the copy. There is no tag, no label, no physical fact that distinguishes them. They are both equally continuous with your past. They are both equally real. If you insist that one of them is really you and the other is just a copy, you are adding something to the physics. You are postulating a fact that goes beyond the mathematics, a fact about which branch carries your personal identity. But there is no such fact. The physics does not contain it. This is where the philosopher Derek Parfit becomes essential. Parfit is best known for his work on personal identity, particularly in his 1984 book, Reasons and Persons. He thought deeply about cases of fission, where a single person splits into two, and his conclusions apply directly to the many worlds interpretation. Parfit asked us to imagine a teletransporter that creates a perfect copy of you on Mars while destroying the original on Earth. Is the person on Mars you? Most people's intuition is that they are not. They are a copy. The real you was destroyed, but now imagine a teletransporter that creates the copy on Mars without destroying the original on Earth. Now there are two people, both with equal claim to being you. The person on Mars has all your memories, all your personality, all your psychological continuity with your past. So does the person on Earth. Which one is really you? Parfit's radical answer is that this question has no answer. It is what he called an empty question. You are not identical to either of them because they are not identical to each other, and identity is transitive. If you were identical to both, they would have to be identical to each other. But they are clearly not. They are two different people who will have different experiences and different futures. So what happened to you? Parfit's answer is that you ceased to exist. Not in the sense that you died. Nothing bad happened to you. Both of your successors are alive and well. They both have psychological continuity with you. They both remember being you. In every sense that matters, they are continuations of you. But you, the single unified person you were before the split, no longer exist. You have been replaced by two successor selves. Parfit argued that this is not actually a bad thing. He said that personal identity is not what matters. What matters is psychological continuity, the persistence of memories and personality, and the things you care about. In a fission case, psychological continuity is preserved in both branches. Everything that matters about you survives. Only the metaphysical fact of your identity as a single person is lost. And that metaphysical fact, Parfit argued, was never very important to begin with. It suggests that we should care less about our future selves being identical to us, and more about whether they will have good lives, whether they will remember us, whether they will carry forward what we valued. But in the context of many worlds, Parfit's view has a darker implication. Because if the universe is constantly branching, and if each branching event is a fission event for you, then you are not a continuous entity moving through time. You are a momentary self that exists for an instant before being replaced by multiple successor selves. What you experience as the flow of time is actually a sequence of destruction and replacement. The you of this moment will not exist in the next moment. Multiple yous will exist, all of them with equal claim to being your continuation, none of them identical to you. The philosopher Emily Qureshi Hurst at Oxford has worked out these implications in detail. She notes that fission satisfies all the normal criteria for personal persistence. The successor selves have psychological continuity, physical continuity, memory continuity. By any standard we normally use, they count as continuations of the original person. But they are not identical to the original, because they are not identical to each other. So what we have is a process that looks like persistence from the inside, but is actually repeated destruction and replacement. Qureshi Hurst draws an uncomfortable conclusion. She says that some philosophers believe that fission means death, not death in the usual sense, where a person ends and no successor exists, but a kind of death where the original person ends and successors exist. The distinction may seem abstract, but it matters, because it means that if many worlds is correct, you are dying billions of times per second. Every quantum event in your brain that could have gone multiple ways is a fission event. Every such event ends the you that existed before it and creates multiple successor selves. You will never experience this. From the inside, each of your successor selves experiences an unbroken stream of consciousness. They remember being you, they feel like you. For all practical purposes, they are you. But metaphysically, the person you were a moment ago is gone, replaced, ended. What exists now are copies who do not know they are copies. And if this seems disturbing, it gets worse. Because the many worlds interpretation does not just say that you are branching into multiple successor selves. It says that you are branching into every possible successor self. Every quantum outcome that is physically possible is realized in some branch. Every version of you that quantum mechanics allows is real somewhere in the branching structure. Think about what that means. In some branches, you make good decisions and live a happy life. In other branches, you make terrible decisions and suffer. In some branches, you die peacefully at an old age. In other branches, you die in agony tomorrow. Every possible future is realized. Everywhere your life could go is happening to some version of you. This includes the worst possibilities. In some branches, versions of you are experiencing the maximum possible suffering that a human nervous system can generate. They are being tortured. They are watching everyone they love die. They are trapped in situations of unbearable pain with no escape. This is not a probability. If many worlds is correct, this is a certainty. 100% of possible horrors are happening, distributed across branches, all equally real. You might think that this is just a feature of probability. In any probabilistic theory, bad outcomes have some chance of occurring, but many worlds is not probabilistic in the ordinary sense. In many worlds, all outcomes occur. The probabilities we observe are not about which outcomes happen, they are about which branches we are likely to find ourselves in. But all branches exist. All outcomes are realized. The suffering is not possible. It is actual. Max Tegmark, one of the most prominent advocates of many worlds, has formulated a thought experiment that drives this point home. It is called the quantum suicide experiment, and it was independently proposed by several people in the late 1980s. The setup is simple. You have a gun connected to a quantum random number generator. Half the time, the generator produces one outcome and the gun does not fire. Half the time, it produces the other outcome and the gun fires, killing you instantly. You point the gun at your head and pull the trigger. In the Copenhagen interpretation, you have a 50% chance of dying on each trial. If you repeat the experiment many times, you will almost certainly die. The probability of surviving 10 trials is less than 1 in 1,000. But in the many worlds interpretation, something different happens. Each time you pull the trigger, the universe branches. In one branch, the gun fires, and you die. In the other branch, the gun does not fire, and you survive. Both branches are real, both outcomes occur. Now consider the subjective experience. In the branches where you die, you have no experience at all. Dead people do not experience anything. But in the branches where you survive, you do have experiences. You notice that you are still alive. You pull the trigger again. If you keep pulling the trigger, you keep branching. Half of your branches end in death, but you can only have experiences in the branches where you are alive. No matter how many times you pull the trigger, the version of you that continues to have experiences is the version in the branches where you keep surviving. From the inside, from the subjective perspective, you always survive. The gun never fires, you pull the trigger 100 times, and you are still alive, marveling at your luck. You have discovered a kind of quantum immortality. You cannot experience your own death because dead versions of you do not experience anything. The only version of you that experiences anything is the version that keeps surviving. This thought experiment is not an argument for actually playing Russian roulette. From a third-person perspective, you are dying in half of all branches every time you pull the trigger. You are killing off huge fractions of your successor selves. The fact that the surviving fractions do not experience the deaths does not make those deaths less real. But the thought experiment reveals something disturbing about the many worlds interpretation. It suggests that there is always some branch where you survive. No matter what happens, some version of you makes it through. Even if you are hit by a bus, or catch a fatal disease, or die of old age, there are branches where you survive. Maybe the bus misses, maybe the disease is caught early, maybe your body keeps functioning a little longer. The probability gets smaller and smaller, but it never reaches zero. Some branch of you is always there. This is quantum immortality, and Hugh Everett himself believed in it. According to biographers, Everett was convinced that his many worlds theory guaranteed him immortality. His consciousness, he argued, would always follow whatever path does not lead to death. He could not experience non-existence, So from his subjective perspective, he would never die. The irony is crushing. Everett believed his theory meant he could never really die, and then he drank himself to death at 51, destroying his body with alcohol and cigarettes and neglect. In the branches where we exist, in the world where you are hearing this, Everett is dead. But according to his own theory, there are branches where he is still alive, branches where he took care of himself, branches where he saw his theory accepted, branches where he is 94 years old right now, watching quantum computing vindicate everything he proposed. We cannot reach those branches, and neither could his daughter Elizabeth, who killed herself hoping to find him. Tegmark, who formalized the quantum suicide thought experiment, now rejects the strong version of quantum immortality. He points out that death is not usually instantaneous. Consciousness does not flip from on to off. It fades. In most realistic scenarios, you do not die instantly. You lose function gradually. Your mind deteriorates, and in those scenarios, there are branches where your brain keeps functioning, but at a degraded level. Branches where you survive, but with severe damage. Branches where you are trapped in a failing body with a failing mind, unable to die, but also unable to live. Quantum immortality, if real, would not be a blessing. It would be a curse. You would never fully die, but you would also never stay healthy. There would always be some branch where your suffering continues just a little longer. Some branch where your body hangs on past the point where life has any value. The logic of quantum immortality leads not to eternal youth, but to eternal decay. But here is the thing that nobody wants to talk about. If many worlds is correct, the horrifying scenarios are not hypothetical. They are not thought experiments. They are happening right now. Somewhere in the branching structure of reality, every version of every person who has ever lived is experiencing every possible variation of their life. The good versions and the bad versions. The happy endings and the nightmarish ones. Right now, there are versions of you that are suffering. Versions that made one different decision and ended up in hell. Versions that got sick, lost everything, experienced unimaginable pain. They are as real as you are. They remember being you. They think they are you, and they are trapped in their branches with no way out. You cannot help them. You cannot reach them. You cannot even confirm they exist. The branches are separate. Decoherence has made them inaccessible. The mathematics that describes the functioning of every quantum computer, every laser, every transistor, also describes them. The same equations that predict the behavior of electrons in semiconductors predict that your suffering doubles are real. And the physicists who accept the many worlds interpretation, who consider it probably correct, who write books and give lectures defending it, have largely chosen not to discuss this. They acknowledge it briefly, they mention it in footnotes, they waver the philosophical implications, and then return to the mathematics. They treat the question of what this means for human existence as somehow separate from the question of whether the physics is right. Sean Carroll, in Something Deeply Hidden, asks whether the branching of our current selves into multiple future selves should affect the choices we make. His answer is that upon careful consideration, it turns out to matter much less than you might guess. This is a remarkable claim. The theory he is defending implies that you are constantly being destroyed and replaced, that infinite versions of you are suffering right now, that personal identity, as commonly understood, is an illusion, and his response is that it does not really matter. Maybe he is right, maybe Parfit is right, maybe what matters is psychological continuity, and since that is preserved in every branch, we should not worry about the metaphysics of personal identity. Maybe the suffering that is happening in other branches is no more our concern than the suffering of strangers in distant countries. Maybe we should focus on the branches we can affect and let the others go, but there is something uncomfortable about the speed with which this conclusion is reached. There is something suspicious about how quickly the physicists move past the implications of their own theory. The same physicists who will spend years analyzing the technical details of the probability problem in many worlds, who will publish papers debating the preferred basis problem and the derivation of the Born rule, somehow have very little to say about what their theory means for the existence of persons. Perhaps they are right that it does not matter. Perhaps the philosophical implications really are separate from the physics. But the silence is still notable. The avoidance is still there. The conclusion about you that nobody was supposed to find remains largely unspoken, even by the people who are most confident that many worlds is true. And there is a history to this silence, a culture of avoidance that predates the many worlds interpretation itself, a deliberate decision by the physics community to stop asking certain questions, a decision that has shaped the field for nearly a century. The phrase, "shut up and calculate," has become the unofficial motto of quantum mechanics. It was coined by David Mermin in a 1989 article in Physics Today, though it is often misattributed to Richard Feynman. The phrase captures the attitude that dominated physics for most of the 20th century. Do not ask what the mathematics means. Do not worry about the interpretation. Just use the equations to make predictions and collect your Nobel Prize. Mermin later said that his professors were indifferent to philosophy. Full stop, quantum mechanics worked. Why worry about what it meant? This attitude was not neutral, it was actively enforced. Jim Baggott documented this history in a 22,000 article in Nature, describing how post-war physicists created an unquestioning orthodoxy by suppressing questions they considered too philosophical. Nobel laureates who continued to express discomfort with the foundations of quantum mechanics were branded as senile by professional gossip. The culture made it clear that foundational questions were a career risk. This culture explains a lot about why Everett's theory was ignored for so long. It explains why the measurement problem was allowed to fester unresolved for decades. And it explains why, even now, the many worlds interpretation can be endorsed by prominent physicists without anyone being forced to confront what it says about personal identity and human existence. Scott Aronson, the quantum computing theorist, has noted that some physicists seem to adopt a position he calls many worlds minus the many worlds. They accept the Everettian formalism. They agree that the wave function never collapses. They accept all the mathematical consequences. But they refuse to acknowledge that this implies the existence of multiple branches, multiple versions of each person, multiple realities. They want the elegant mathematics without the strange metaphysics. But you cannot have one without the other. The mathematics is the metaphysics. If the wave function is real and it never collapses, then the branches are real. The multiple versions of you are real. The suffering that is happening in other branches is real. You can refuse to talk about it. You can change the subject. You can insist that philosophy is not your department, but you cannot make it go away by ignoring it. And so we arrive at the question that has been implicit throughout this video. The question that physicists have avoided for decades. The question that the many worlds interpretation forces us to confront, whether we want to or not. If this theory is true, what does it mean to be you? You are not a continuous entity. You are a branching structure. The person who woke up in your body this morning is already gone, replaced by billions of successor selves who think they are still you. The person who will fall asleep tonight is not the same person who is watching this video. They share your memories, they continue your psychological story, but they are not numerically identical to you. You have ended and been replaced countless times since this video began. You do not have a single future. You have infinitely many futures. Every possible outcome of every quantum event that occurs in your vicinity creates a branch. In some of those branches, you prosper. In others, you suffer. In some, you make good choices. In others, you make every terrible decision a human can make. They are all you in the sense that they all have psychological continuity with the person you are now. But none of them is the single unique you that you intuitively believe yourself to be. And somewhere in the branching structure of reality, versions of you are experiencing things you do not want to think about, pain you cannot imagine, loss you cannot comprehend, horror you cannot conceive. They are not metaphors, they are not possibilities. If many worlds is correct, they are actualities. They are happening now to people who remember being you, in branches just as real as this one. The mathematics is settled. The decoherence is confirmed. The branches are real. The only question is whether you can accept what this means for your existence, whether you can live with the knowledge that you are not what you thought you were, whether you can face the conclusion about you that nobody was supposed to find, and whether in some branch somewhere there is a version of you who learnt all this and found a way to make peace with it, or whether in this branch you are left with the weight of knowing that you are one of infinitely many, that your story is one of infinitely many stories, that your suffering is one instance of infinite suffering. In 1996, Elizabeth Everett made her choice. She believed in her father's theory. She believed that disposing of her ashes the same way he had disposed of his would help her reach him. She believed that death was not an ending, but a doorway between branches. If many worlds is correct, she was right about the physics. There are branches where Hugh Everett is alive. There are branches where Elizabeth is alive with him. There are branches where the theory was accepted and the family was whole, and the man who saw the truth about reality did not drink himself to death in obscurity. But those branches are not this one, and the branches are separate, and we cannot reach across the gaps that decoherence has opened. We are trapped in our branch, knowing that other branches exist, unable to touch them, unable to help the versions of ourselves who are suffering in them, unable to join the versions who are thriving. That is what the many worlds interpretation actually says. That is the conclusion about you that nobody was supposed to find. And now that you know it, you have to decide what to do with it. There is a question that physicists rarely ask about the many worlds interpretation, but that you should ask. The question is simple. If this theory is true, what happens to morality? Think about it. If every choice you could possibly make is made in some branch, then what does it mean to make the right choice? When you face a moral decision, when you choose kindness over cruelty or honesty over deception, you are not preventing the cruel or deceptive outcome. You are just ensuring that the version of you in this branch is the kind or honest one. In another branch, another version of you made the opposite choice. That version exists. That version is as real as you are. The cruelty happened, the deception happened. Your choice did not prevent it. Some philosophers have argued that this makes many worlds morally catastrophic. If every possible action is taken by some version of you, then you are already a murderer in some branch. You are already a saint in another branch. The total moral weight of your existence, summed across all branches, is fixed. Nothing you do changes it. Your decisions just determine which branch you find yourself in, not whether the bad outcomes occur. Emily Qureshi-Hurst at Oxford has explored this problem in depth. She notes that many worlds threatens two conditions that most philosophers consider necessary for moral responsibility. The first is the continued existence of the self. If branching means you are constantly being destroyed and replaced, if the you of this moment is not identical to the you of the next moment, then who is responsible for your actions? The successor selves who emerge from your choices did not make those choices. They inherited them, and the self who made the choices no longer exists. The second condition is freedom. If the universe is deterministic at the level of the wave function, if every branch that is quantum mechanically possible actually occurs, then what room is there for free will? You might feel like you are choosing, but the branching structure was determined by the initial conditions of the universe. Every choice you will ever make was already implicit in the wave function at the Big Bang. You are not deciding the future, you are just discovering which branch you occupy. Qureshi Hearst worries about what she calls a careless attitude that many worlds might encourage. If you know that some version of you survives every possible disaster, you might be tempted to take risks you otherwise would not take. If you jump off a cliff, yes, you will die in many branches, but there will be branches where you survive. Some version of you will be fine. Does that make the jump less bad? The answer is obviously yes. It is still bad. The versions of you who die still die. The suffering still happens. But the many worlds framework makes it harder to articulate why it is bad. The total amount of death across all branches is not changed by your choice. Your choice just affects which branch you experience. David Deutsch has attempted to rescue free will and moral responsibility within the many worlds framework. He argues that knowledge creation is a real phenomenon that shapes which branches are realized in which ways. When you make a choice based on understanding, based on reasoning, based on knowledge of good and bad, you are doing something that affects the branching structure in a meaningful way. The branches where you act wisely are not just random, they are the product of something real, something that Deutsch calls explanation. And this, he argues, is enough to ground morality and meaning. Sean Carroll takes a different approach. He argues that you should not care about what happens in other branches because you cannot affect them. Your choices affect this branch. The fact that other branches exist does not change your moral obligations here. It just means that morality is local to a branch rather than global across all branches. But there is something unsatisfying about this response. It feels like it is just stipulating that you should not care about other branches, without explaining why. If the versions of you in other branches are as real as you are, if they have your memories and your personality and your claim to being you, why should you not care about them? If you would be devastated to learn that a loved one is suffering in this branch, why should you be indifferent to learning that a loved one is suffering in another branch? The many worlds proponents do not have a good answer to this. They acknowledge the problem and then move on. They treat the moral implications as less important than the physics. But the moral implications are not separate from the physics. They are part of what it means for the physics to be true. And there is another implication that nobody wants to discuss. If many worlds is true, then there are branches where you do terrible things. Not just branches where you make small bad choices, but branches where you commit atrocities. For any action that is quantum mechanically possible, there is a branch where you perform it. The version of you in that branch had the same starting point as you. They share your history up to the branching event. And then they did something unspeakable. Those versions of you exist. They are as real as you are. They have your memories, your personality, everything that makes you you up to the point of divergence. And then they became monsters. How do you live with that knowledge? How do you accept that you are one version of a branching structure that includes every possible version of you, including the worst ones? How do you maintain a sense of self when that self is distributed across infinite branches, some of which contain people you would be horrified to know? The physicists do not address this. It is not a physics question, they would say. It is philosophy. It is psychology. It is someone else's problem. If many worlds is true, it is everyone's problem. And the silence from physicists does not make the problem go away. It just means you have to face it without help. But deciding what to do with it requires first asking whether it is true. And this is where the physics community fractures, because the many worlds interpretation, for all its elegance, for all its mathematical simplicity, faces objections that even its supporters acknowledge are serious. The question is whether those objections are fatal or whether they are the kind of problems that any sufficiently radical theory must work through. The most damaging objection is called the probability problem, and it cuts right to the heart of what many worlds is supposed to explain. Here is the issue. Quantum mechanics makes probabilistic predictions. When you measure an electron's spin, the theory tells you the probability of getting spin up versus spin down. These probabilities are given by something called the Born rule, which says that the probability of an outcome equals the square of the amplitude of that component of the wave function. The Born rule has been tested to extraordinary precision. It is the empirical core of quantum mechanics. But in the many worlds interpretation, all outcomes occur, every branch is real. So what does probability even mean? If both spin up and spin down happen with certainty, in what sense is one more probable than the other? The standard many worlds answer is that probability should be understood as self-locating uncertainty. Before the measurement, you do not know which branch you will find yourself in afterward. The Born rule tells you the probability that you will be the version who observes spin up versus the version who observes spin down. Both versions exist, but you do not know which one you are until you look. David Deutsch and David Wallace have developed elaborate decision-theoretic arguments for why a rational agent in an Everettian universe should bet according to the Born rule. Sean Carroll and Charles Sebens have proposed that the Born rule follows from how you should assign credences when you are uncertain about your location in a branching structure. Wojciech Zurek has derived the Born rule from symmetries of entangled quantum states. Multiple approaches, multiple derivations, all arriving at the same answer. But critics are not convinced. David Albert, a philosopher of physics at Columbia, invented what he calls the fatness measure to illustrate the problem. The fatness measure says that probability should be proportional to the mass of the observer in each branch. A heavier version of U should be more probable than a lighter version. This sounds absurd. But Albert's point is that many worlds gives you no principled reason to prefer the Born rule over the fatness measure. Both are consistent with the mathematics. Both assign probabilities to branches. Why is one right and the other wrong? The many worlds proponents have responses to this. They argue that the Born rule is uniquely picked out by certain rationality constraints or by the structure of quantum mechanics itself. But the debate continues. Klaas Landsman, in a comprehensive survey of the probability problem, concluded that no generally accepted derivation of the Born rule has been given to date. This is not a minor technical issue. It is a question about whether many worlds can actually account for the empirical success of quantum mechanics. The second major objection is called the preferred basis problem. When the universe branches, it branches into specific states. The electron is spin up in one branch and spin down in another. The cat is alive in one branch and dead in another. But why those states? Why not some bizarre superposition of spin up and spin down? Why not a branch where the cat is in some mathematically definable combination of alive and dead that does not correspond to anything we would recognize? The mathematics of quantum mechanics does not single out any particular set of states as special. You can describe the same wave function in terms of different bases, different ways of carving up the possibilities. The spin up and spin down basis is not mathematically privileged over some other basis that mixes them together. So why does the universe branch into the states we observe, rather than some other set of states? The standard answer appeals to decoherence. When a quantum system interacts with its environment, certain states are stable against decoherence and others are not. The states that survive are the ones that do not get scrambled by environmental interactions. This is called einselection, short for environment-induced superselection. The environment effectively chooses the basis in which branching occurs. But critics argue that this answer is circular. Decoherence depends on probabilities. The stability of certain states depends on how likely certain interactions are. And if probabilities are what we are trying to explain, we cannot use them to explain the basis problem. without going in a circle. Meyer Hemo and Orly Schenker published a paper in 2022 arguing that decoherence cannot solve the preferred basis problem because decoherence itself presupposes the ontology that the preferred basis problem is supposed to establish. Henry Stapp, a physicist at Lawrence Berkeley National Laboratory, put it bluntly. He said that a many-worlds interpretation of quantum theory exists only to the extent that the associated basis problem is solved. If you cannot say which states the universe branches into, you have not actually given a complete interpretation. You have just pushed the mystery around. The third objection is unfalsifiability. The many-worlds interpretation makes the same predictions as the Copenhagen interpretation for all feasible experiments. The other branches are inaccessible. Decoherence has made them unreachable. No experiment can detect them. So how is this different from postulating invisible unicorns? How is it science rather than metaphysics? Many worlds proponents have several responses. First, they point out that the other interpretations are equally unfalsifiable. Copenhagen cannot experimentally distinguish itself from many worlds either. The choice between interpretations is not made by crucial experiments, but by theoretical virtues like simplicity, coherence, and explanatory power. Second, some proponents argue that many worlds could in principle be tested. David Deutsch has proposed thought experiments involving observers placed in coherent superposition. If you could put a human brain in a superposition and then bring the branches back together, you could in principle observe interference effects that would confirm many worlds. The fact that this is technologically impossible does not make it scientifically meaningless. General relativity makes predictions about the interior of black holes that we cannot test either, but we do not dismiss those predictions as unscientific. Third, proponents argue that many worlds makes indirect predictions through quantum computing. If quantum computers achieve speedups that cannot be explained by classical physics, and if the many worlds picture provides the most natural explanation for how those speedups are achieved, that is a kind of evidence. Not proof, but evidence. Critics find these responses inadequate. Roger Penrose calls many worlds a reductio ad absurdum, an example of what happens when you take a mathematical formalism too literally. Gerard Hooft says he does not believe we have to live with the many worlds interpretation, that the stupendous number of parallel worlds exists only because physicists could not decide which one is real. Sabine Hossenfelder argues that many worlds does not actually solve the measurement problem because a detector that also splits gives the answer anything that is possible with probability. 1. These objections are serious. The probability problem, the preferred basis problem. They have not been definitively solved. The many worlds interpretation is not a finished theory with all the details worked out. It is a research program, a framework, a way of thinking about quantum mechanics that may or may not pan out. But here is what the critics often fail to acknowledge. The other interpretations have problems too. Copenhagen has the measurement problem, the inability to say what collapse is or when it happens. Pilot wave theory has non-locality problems that make it incompatible with special relativity. Objective collapse theories introduce new physics that has never been observed. Every interpretation of quantum mechanics has issues. The question is not whether many worlds is perfect. The question is whether it is better than the alternatives. And when you survey physicists, you find something remarkable. There is no consensus. The most successful theory in the history of science, and the people who use it every day, cannot agree on what it means. Sean Carroll calls this the most embarrassing graph in modern physics. When you plot how physicists answer the question of which interpretation they prefer, you get a scattered mess with no clear winner. The surveys tell a consistent story. In 1997, Max Tegmark conducted an informal poll at a quantum mechanics workshop. Copenhagen got 27%. Other interpretations and undecided made up the rest. In 2011, a more formal survey at an Austrian conference found Copenhagen at 42% and many worlds at 18%. In 2013, a survey at a Quantum Foundations conference found Copenhagen and many worlds roughly tied, with each getting about a quarter of the votes. In 2205, a Nature survey found Copenhagen at 36% and many worlds at 15%. The numbers vary depending on who you ask. Quantum Foundations specialists tend to favor many worlds more than physicists in general. Younger physicists tend to favor it more than older ones. The trend over time has been towards many worlds gaining ground, though Copenhagen remains the plurality choice in most surveys. But the striking thing is not which interpretation is winning. The striking thing is that no interpretation is winning. After 100 years, physicists cannot agree on what quantum mechanics is telling us about reality. They can agree on the equations, they can agree on the predictions, but they cannot agree on what the equations mean. This should disturb you. This should disturb everyone. We have a theory that describes the fundamental behavior of matter and energy, a theory that underlies all of chemistry and most of physics, a theory that makes technology possible, and we do not know what it is saying about the world. We do not know whether reality is constantly branching, or whether wave functions collapse, or whether hidden variables guide particles along definite paths. We have been using this theory for a century, and we still do not understand it. The many worlds interpretation is one attempt to understand it. It may be right, it may be wrong, but it is taken seriously by a significant minority of physicists, including some of the most prominent names in the field. And if it is right, then everything I have told you about personal identity and branching and suffering is true. Not metaphorically true, literally true. As true as the predictions of quantum mechanics that make your phone work. So why do physicists not talk about this? Why is the question of what many worlds means for human existence treated as a footnote rather than a headline? Why can Sean Carroll write an entire book defending many worlds and spend only a few pages on the implications for personal identity? Part of the answer is disciplinary boundaries. Physicists think of themselves as studying the physical world, not the nature of persons. Questions about identity and consciousness and the meaning of existence are philosophy, not physics. When a physicist derives the decoherence timescale for a macroscopic object, they are doing physics. When they ask what it means for you to split into multiple copies, they have crossed into territory where they do not feel qualified. But this boundary is artificial. If physics tells us that reality branches, and if branching has implications for personal identity, then physics has something to say about personal identity, whether physicists want it to or not. You cannot propose a theory about the structure of reality and then disclaim responsibility for its implications. The implications are part of the theory. Part of the answer is the shut up and calculate culture I mentioned earlier. Physicists are trained to focus on the mathematics and avoid interpretive questions. This training served the field well in some ways. It allowed quantum mechanics to develop rapidly without getting bogged down in philosophical disputes. But it also created a culture where asking big questions is seen as unserious, where wondering what your theory means for human existence is treated as a distraction from real physics. And part of the answer, I suspect, is that the implications are genuinely disturbing. It is one thing to accept that reality branches. It is another thing to accept that you are being destroyed and replaced billions of times per second. It is one thing to acknowledge that many worlds implies infinite suffering. It is another thing to sit with that knowledge and think about what it means for the people you love. Physicists are human. They have the same psychological defenses as everyone else. And when a theory implies something horrible, the natural response is to look away, to focus on the technical details, to treat the disturbing implications as someone else's problem. but the implications do not go away because you ignore them. If many worlds is true, then everything I have described is happening right now. The branching is occurring, the copies are being created, the suffering is real. Your refusal to think about it does not make it less true, it just makes you someone who is ignoring the truth. And this brings us back to the Everett family, because the tragedy of Hugh Everett is not just that his theory was ignored, it is that his theory, if true, makes his tragedy infinitely worse. Hugh Everett died in 1982, alone in his bed, having destroyed his body with alcohol and neglect. His son Mark found his corpse the next morning. The body was cold and stiff. Mark later said that touching his father was the first physical contact between them that he could remember. After Everett's death, his wife Nancy kept his ashes in a filing cabinet. For years, they sat there in a box in a filing cabinet in the house where he had drunk himself to death. Eventually, she threw them in the trash, as he had requested. His remains went out with the garbage. The man who had proposed that reality constantly branches ended up in a landfill somewhere, mixed with coffee grounds and junk mail. Nancy Everett died of cancer in 1998. She had also been a heavy smoker. She had also struggled with depression. By the time she died, 2 of the 3 people in the Everett family photographed from the Copenhagen trip in 1959 were gone. Elizabeth had killed herself 2 years earlier. Only Mark remained. Mark Oliver Everett became a rock musician. He is the frontman of a band called Eels. His songs are often about loss, about grief, about the difficulty of connecting with other people. He wrote an album called Electroshock Blues after his mother's death and his sister's suicide. The album is about trying to survive when everyone around you is gone. In 2007, Mark made a documentary for the BBC called Parallel Worlds, Parallel Lives. The documentary follows him as he tries to learn about his father's work and legacy. He interviews physicists who knew Hugh Everett. He visits Princeton. He reads his father's papers. He tries to understand the theory that consumed his father's life and that his sister invoked in her death. At one point in the documentary, Mark visits a physicist who explains the many worlds interpretation to him. The physicist describes how reality branches, how every outcome occurs, how there are countless versions of each person across the branching structure. Mark listens carefully, and then he asks the question that the physicist probably did not expect. He asks whether this means his father is still alive somewhere, in some branch, in some version of reality. The physicist pauses. Then he says yes. If many worlds is correct, there are branches where Hugh Everett did not die, branches where he took care of himself, branches where he is still alive. Mark's reaction is complicated. There is something comforting in the idea that his father exists somewhere, in some form, but there is also something painful, because that version of his father is unreachable. That version of his father exists in a branch that Mark cannot access. The father who might have been there for him, who might have explained his theories, who might have been more than a lump of furniture at the dining room table, exists somewhere, but not here, not in this branch. If many worlds is true, the Everett family tragedy has infinite echoes. There are branches where Hugh lived to see his theory vindicated. There are branches where Elizabeth got the treatment she needed and survived. There are branches where Nancy did not get cancer. There are branches where Mark grew up with a father who was present, who engaged with his children, who was happy. But there are also branches where things went worse. Branches where Hugh died even younger. Branches where Elizabeth's first suicide attempt succeeded. Branches where the whole family was destroyed in ways that we cannot imagine. The mathematics does not favor the good branches over the bad branches. Both exist. Both are real. And here is something that almost nobody mentions about the Everett family. Mark had a cousin named Jennifer. Jennifer Lewis was a flight attendant for American Airlines. On 9/11/2001, she was working on Flight 77. That was the plane that the hijackers flew into the Pentagon. The building where Hugh Everett had worked for most of his career. The building where he had calculated nuclear fallout patterns and advised presidents on mutually assured destruction. His niece died when a plane struck the building where he had spent his professional life. In the many worlds interpretation, there are branches where Flight 77 was not hijacked, branches where Jennifer Lewis landed safely, branches where she is still alive, still flying, still part of what remains of the Everett family. But those branches are not this one. Mark Everett is the sole surviving member of his immediate family. His father, mother, and sister are all dead. His cousin died in a terrorist attack. The man who proposed that reality branches into countless versions has a son who is utterly alone in this particular branch. If many worlds is true, Mark has counterparts in other branches who are not alone, counterparts whose families survived, counterparts who grew up with present fathers and healthy sisters and living mothers. But Mark cannot reach them. He cannot even confirm they exist. All he has is the mathematics, the theory that his father proposed and that the physics establishment ignored, telling him that somewhere, in some branch, things are different. This is what many worlds means for real people, not the whimsical version where there is a universe where you are a rock star, the real version, the version where your family is dead in this branch and alive in another, and you can never reach them. The version where your suffering is one instance of infinite suffering. The version where the people you love are being tortured in some branch right now, and there is nothing you can do about it. The physicists who accept many worlds know this. They understand the mathematics. They understand what infinite branching implies. And for the most part, they do not talk about it. Let me be clear about what I am not saying. I am not saying that physicists are bad people for not dwelling on the horrifying implications of their theories. I am not saying that Sean Carroll or David Deutsch or Max Tegmark are doing something wrong by focusing on the physics rather than the existential horror. The physics is important. Understanding quantum mechanics is important. And it may not be psychologically possible to do physics while constantly thinking about the infinite suffering that your theory implies. But I am saying that there is a gap between what the theory says and what physicists are willing to discuss. There is a silence around the implications. There is an unspoken agreement to change the subject when the conversation gets too dark. And that silence is worth noticing. That silence tells you something about what it means to live with this theory, to accept it as probably true while still getting out of bed in the morning and doing physics. Maybe the silence is the right response. Maybe the implications are so overwhelming that the only healthy thing to do is compartmentalize. Maybe the people who think about this too much are the ones who end up paralyzed, unable to function, unable to do the work that might eventually tell us whether many worlds is true. But maybe the silence is also a kind of cowardice, a refusal to face what the theory actually says, a way of enjoying the intellectual elegance of many worlds while avoiding its emotional weight. I do not know which it is. I do not know how you are supposed to live with the knowledge that infinite versions of you are suffering right now, if that knowledge is true. I do not know how you are supposed to make choices when every choice is made in some branch. I do not know how you are supposed to care about the future when every possible future is equally real. These are not physics questions. They are questions about how to be a person in a universe that may not have been designed with persons in mind. And physics does not answer them. Physics tells you what is true. It does not tell you how to live with the truth. What I do know is this. The many worlds interpretation is taken seriously by serious physicists. It may be the correct description of reality. And if it is, then you are not who you think you are. You are not a single continuous person moving through time. You are a constantly branching structure, splitting and resplitting, creating new versions of yourself that diverge and never reunite. The you of this moment will not exist in the next moment. What will exist are successor selves, countless successor selves, each experiencing their own branch, each thinking they are the original, none of them identical to the person you are right now. You do not have a single future. You have infinitely many futures. In some of them, you flourish. In others, you suffer unbearably. All of them are real. All of them are happening. The good outcomes do not cancel out the bad outcomes. They coexist eternally in the branching structure of the wave function. And somewhere in that structure, right now, versions of you are experiencing things that you do not want to think about. They are you in every sense that matters. They have your memories, your personality, your sense of self. They woke up this morning thinking they were you. And now they are living through nightmares. You cannot reach them, you cannot help them, you cannot even prove they exist. But the mathematics says they are there. The same mathematics that predicts the behavior of transistors and lasers and quantum computers says that your suffering doubles are real. This is the conclusion about you that nobody was supposed to find. This is what the many worlds interpretation actually says. When you follow it through to the end, when you take it seriously as a description of reality rather than a mathematical curiosity. And the physicists who accept this theory, who consider it probably correct, who think it is the best explanation for the behavior of quantum systems, have mostly chosen not to dwell on this. They acknowledge it and move on. They mention it in passing and change the subject. They treat the horror as a footnote to the elegance. Maybe they are right to do so. Maybe focusing on the horror would be paralyzing. Maybe the only way to function is to compartmentalize, to do the physics and not think too hard about what it means. But you do not have that luxury. You are not a physicist. You do not have equations to hide behind. All you have is the knowledge that some of the smartest people in the world think reality works this way, and now you have to figure out what to do with that knowledge. I cannot tell you what to do. I cannot tell you how to live with this. But I can tell you what Elizabeth Everett did. In 1996, after years of struggling with mental illness, she made a decision. She wrote a note explaining what she wanted done with her remains. She asked to be cremated. She asked not to be kept in an urn or a filing cabinet. She asked for her ashes to be thrown in the garbage. And then she wrote something that shows she understood her father's theory, understood it deeply, understood what it meant. She wrote that she hoped disposing of her ashes this way would help her end up in the correct parallel universe to meet up with Daddy. She believed that her father was alive somewhere, in some branch, in some version of reality. She believed that death was not the end, but a transition between branches. She believed that if she could just find the right way to go, she might reach him. The physics does not support this belief. Decoherence separates the branches. There is no known mechanism for moving between them. Death in one branch does not transport you to another branch. It just ends your existence in that branch. The versions of you in other branches continue, but they were always there. Your death does not create them or connect you to them. But Elizabeth Everett believed anyway. Maybe the belief was a symptom of her illness. Maybe it was a desperate hope that gave her the courage to end her pain. Maybe it was the only way she could make sense of a theory that says reality branches infinitely, while you are trapped in a single branch watching your life fall apart. Her ashes were disposed of as she requested, thrown away like her father's. The daughter who wanted to find her father in another universe ended up in the same place he did. A landfill somewhere, mixed with garbage, gone. If many worlds is true, there are branches where Elizabeth Everett is alive, branches where she got better, Branches where she found her father, not in death, but in life, in a timeline where he did not drink himself into an early grave. Those branches exist. Those versions of Elizabeth and Hugh exist. But we cannot reach them, and neither could she. That is the weight of many worlds. That is what it means to take this theory seriously. It means knowing that better versions of reality exist, versions where the people you love are safe and happy, and knowing that you can never reach them. It means knowing that worse versions exist too, versions where your suffering has no limit, and knowing that those versions are as real as you are. It means living with the knowledge that you are one of infinitely many, that your story is one of infinitely many stories, that nothing you do changes the total amount of suffering in the branching structure, because every outcome happens regardless of your choices. The physicists who accept many worlds have found ways to live with this. They focus on their branch. They make choices as if those choices matter. They care about the people around them, even knowing that other versions of those people are suffering in other branches. They compartmentalize. Maybe that is the only way. Maybe the alternative is paralysis. Maybe the alternative is despair. But I think you deserve to know what the theory actually says. I think you deserve to know that when physicists talk about many worlds, they are not just talking about a mathematical formalism. They are talking about a picture of reality where you are constantly being destroyed and replaced, where infinite versions of you exist in infinite states of joy and suffering, where the boundaries of yourself dissolve into a branching tree that extends forever in all directions. And I think you deserve to know that the man who proposed this theory, the man who saw the solution to the measurement problem when he was 23 years old, spent the rest of his life ignored by the physics establishment, estranged from his children, drinking himself to death in a house in Virginia. And I think you deserve to know that his daughter, who grew up in that house, who watched her father become a ghost, who struggled with mental illness for most of her adult life, died believing that his theory was true, believing that he was alive somewhere, in some branch, waiting for her, believing that death might be a doorway. The mathematics says the branches exist. The mathematics says they cannot communicate. The mathematics says Elizabeth Everett's hope was based on a misunderstanding of her father's theory. But the mathematics also says that somewhere, in some branch, there is a version of Hugh Everett who did not drink himself to death, a version who lived to see his theory accepted, a version who watched his daughter grow up healthy and happy, a version who explained his ideas to his son instead of sitting silent at the dining room table, a version who is alive right now, in some branch we cannot reach, wondering what his life might have been like if things had gone differently. That version of Hugh Everett exists, if many worlds is true. He is as real as you are. He has all the memories of the young physicist who proposed the universal wave function in 1957. He just branched into a better timeline. But he is not here. He is not in this branch. In this branch, Hugh Everett is ashes scattered in a landfill. In this branch, Elizabeth Everett is ashes scattered somewhere else. In this branch, the theory that should have revolutionized physics was ignored for decades, while its creator destroyed himself. And in this branch, you are watching a video about a theory that might be true. A theory that says you are constantly branching. A theory that says infinite versions of you exist. A theory that says some of those versions are suffering unimaginably right now. A theory that the smartest physicists in the world cannot agree on, that the establishment tried to suppress, that the man who invented it believed guaranteed his own immortality. There is something else you should know, something that makes the many worlds picture even stranger, even more difficult to accept. The branches are not created equal. When physicists talk about many worlds, they often give the impression that branching is symmetric. You measure an electron spin, the universe splits, and there are now two branches of equal weight. One where you saw spin up, one where you saw spin down, both equally real. both equally you. But that is not quite right. The branches have different amplitudes, different weights in the wave function. The branch where you observe the more probable outcome has a larger amplitude than the branch where you observe the less probable outcome. This is how many worlds accounts for the Born rule probabilities. The probabilities correspond to the squared amplitudes of the branches. What does this mean? It means the branches are not all the same. Some branches are in some sense more real than others, or at least they have more weight, more presence in the wave function, more of whatever it is that makes a branch a branch. This creates conceptual problems that physicists have struggled with for decades. If you are in a branch, do you experience that branch more if it has higher amplitude? Does it feel different to be in a high amplitude branch versus a low amplitude branch? The answer seems to be no. From the inside, every branch feels the same. You have no way of knowing whether you are in a probable branch or an improbable one. The amplitude is invisible to you. But then what is the amplitude doing? If it does not affect your experience within a branch, why should you care about it? Why should you prefer to be in a high amplitude branch? The decision theoretic arguments for the Born rule attempt to answer this. They say that a rational agent should care about amplitude, because amplitude determines the measure of branches. You should expect to find yourself in high amplitude branches more often because there is more of you, in some sense, in those branches. But this reasoning is contested. Critics say it is circular. Critics say it assumes what it is trying to prove. And there is a deeper puzzle. If every branch is equally real from the inside, if every version of you has the same subjective experience of being real, then what does it mean for some branches to have higher amplitude? Are the low amplitude versions of you less real? Are they less conscious? Do they matter less morally? Nobody has a good answer. The proponents of many worlds typically say that amplitude is like probability, that you should weight your concern for different branches by their amplitudes. But this seems to imply that the versions of you in low amplitude branches matter less, that their suffering counts for less. This is morally uncomfortable. If you take many worlds seriously, you have to confront the possibility that some versions of you are, in some hard-to-specify sense, less important than others. Not because of anything they did, not because of any choice they made, just because of the mathematics of quantum mechanics. Or maybe the amplitude weights are not about importance at all. Maybe they are about something else entirely, something we do not have concepts for. Maybe the question of how to interpret amplitude is as deep and unresolved as the measurement problem itself. The physicists do not dwell on this. They treat amplitude as a mathematical feature of the theory and move on to calculating things. But if you are trying to understand what many worlds means for your existence, for your identity, for the moral weight of your choices, you cannot ignore it. The amplitude structure of the wave function is part of what the theory says about reality, and nobody really knows what it means. There is also the question of how many branches there are. When people hear about many worlds, they often imagine a finite number of parallel universes, 2 branches when you measure a spin, 4 branches when you measure 2 spins, a large but countable number of branches as the universe evolves. But that is not what the mathematics says. The wave function is continuous. It does not branch into discrete chunks. What looks like branching is actually the emergence of approximately independent components through decoherence. The number of branches is not well defined. It depends on how you count. It depends on what you consider a branch. Some say the question is meaningless. Some say the branches are not fundamental, that they are emergent features of the wave function that become approximately well-defined only when decoherence is strong enough. This matters for thinking about personal identity and suffering. If there are infinitely many branches, and you exist in infinitely many of them, what does it mean to say that you are suffering in some branches? Are there infinitely many suffering yous? Are there infinitely many happy yous? Does the infinity of good cancel out the infinity of bad? The mathematics of infinity is strange. An infinite set can contain an infinite subset and still have room for other infinite subsets. There can be infinitely many branches where you suffer and infinitely many branches where you flourish, and both statements can be true simultaneously. The total does not balance out. There is no total. Infinity does not work that way. This is part of why the moral implications of many worlds are so hard to think about. Our intuitions about harm and benefit assume finite quantities. More suffering is worse than less suffering. More happiness is better than less happiness. But if everything is infinite, these comparisons break down. We do not have the conceptual tools to evaluate infinite outcomes. And yet the physicists who accept many worlds live their lives as if finite considerations matter. They make choices. They try to reduce suffering. They act as if the world they are in is the one that counts. Maybe this is the only psychologically viable approach. Maybe the alternative is paralysis. But there is something intellectually dishonest about accepting a theory and then ignoring its implications when those implications become inconvenient. If many worlds is true, the infinities are real. The moral framework that served us in a single finite universe may not apply anymore. And pretending otherwise is just another form of looking away. Let me tell you about another aspect of the many worlds interpretation that rarely gets discussed: the relationship between consciousness and branching. When the universe branches, what happens to your stream of consciousness? Do you experience a continuous flow that goes into one branch? Do you split into two streams that were somehow unified before? The mathematics does not address this directly. The wave function describes physical states, not conscious experiences. How consciousness relates to the branching structure is a question that many worlds does not answer. Some philosophers have argued that this is a fatal problem. They say that any interpretation of quantum mechanics must account for the fact that we experience definite outcomes. We do not experience superpositions. We do not feel ourselves branching. Whatever is happening in the physics, our conscious experience is of a single world with single outcomes. Many worlds says this is because we are inside a branch. From the inside, each branch looks like a single world. But this raises the question of what attaches consciousness to a branch. What makes your conscious experience go with one branch rather than another? What is the mechanism by which your awareness ends up in a particular component of the wave function? The many worlds proponents typically say there is no mechanism because there is no selection. You do not end up in one branch rather than another. You end up in all of them. The versions of you in each branch all have conscious experiences. The sense that you ended up in this branch, that you could have been in a different branch, is an illusion. There was no lottery, all outcomes occurred. All yous are experiencing their respective branches. But this answer is hard to accept. It feels like there is a fact of the matter about which branch you are in. It feels like this branch, the one where you are watching this video and hearing these words, is the real one, the one that matters, the one that is yours. This feeling may be an illusion. The mathematics says all branches are equally real, but the feeling is persistent, and the many worlds interpretation offers no explanation for why the feeling exists, why consciousness seems to track a single branch, why we never experience the branching itself. David Chalmers, the philosopher who coined the term hard problem of consciousness, has written about the relationship between many worlds and consciousness. He notes that many worlds makes the hard problem even harder. It is already difficult to explain how physical processes give rise to conscious experience. It is even more difficult to explain how a branching physical structure gives rise to the specific experience of being in one branch rather than all of them. Chalmers suggests that we may need a new framework to understand consciousness in a many worlds universe. The old questions about the relationship between mind and matter become even more complex when matter is constantly branching. The self becomes a tree rather than a thread. The stream of consciousness becomes a river delta spreading in all directions. None of this has been worked out. The intersection of many worlds and consciousness studies is almost unexplored territory. The physicists say consciousness is not their department. The consciousness researchers say quantum mechanics is not theirs. The questions fall between disciplines, and nobody picks them up. But you are conscious. You are experiencing this moment. If many worlds is true, then your consciousness is somehow embedded in a branching structure that extends infinitely in all directions. Understanding what that means for your experience, for your identity, for the continuity of your mental life, is not optional, it is forced on you by the theory. And the theory provides no guidance. This is part of what it means to live in the gap between physics and everything else. The physics tells you that reality branches. It does not tell you how to understand your own existence in a branching reality. It does not tell you whether you should mourn for the yous who suffer in other branches. It does not tell you whether the you of this moment will have any connection to the you of the next moment. It just describes the wave function and leaves you to figure out the rest. And the man who created this situation, the man who proposed that reality branches and forced us to confront these questions, he could not figure it out either. Hugh Everett spent the last 26 years of his life not doing physics. After Copenhagen rejected him, after Wheeler abandoned him, after his paper was ignored for decades, he worked for defense contractors calculating nuclear war scenarios. He got rich. He started his own company. He had a family that he barely interacted with. He ate and drank himself toward an early grave. Did he think about the implications of his theory during those years? Did he lie awake at night wondering what branching meant for his identity, his mortality, his children? We do not know. He did not write about it. He did not talk about it, at least not to anyone who recorded what he said. What we know is that he believed in quantum immortality. He believed that consciousness could not experience its own termination. He believed that from his subjective perspective, he would always find himself in a branch where he survived. Death was something that happened to other people or to other versions of himself. The version doing the experiencing would go on forever. This belief may have contributed to his self-destruction. If you truly believe you cannot die, at least from your own perspective, why take care of your body? Why worry about heart disease or liver failure or any of the things that kill people? You will always find yourself in the branch where you survived. The versions that die are not you anymore. They are branches that have been pruned from your subjective tree. This logic is seductive and possibly fatal. Max Tegmark, who formalized the quantum suicide thought experiment, has argued strenuously against taking quantum immortality seriously. He points out that most deaths are not instantaneous. You do not flip from alive to dead in a single quantum event. You decay. You deteriorate. Your consciousness fades rather than stops. In a many worlds universe, this means there are branches where you survive but in terrible condition. Branches where your brain is damaged but not destroyed. Branches where you persist in a state of suffering that goes on, because there is always some branch where you survive a little longer. Quantum immortality is not eternal youth. It is eternal decay. It is the worst case scenario, not the best. Did Everett understand this? Did he realize that his belief in quantum immortality might not be the comfort it seemed? We cannot ask him. He died in 1982, alone in his bed, his body finally giving out after years of abuse. His son, Mark, found the body. Mark was 18 years old. He had never really known his father. The man who had proposed that reality branches into infinite versions had been absent from his own family, present in body but unreachable in every other way. Mark later said that his father seemed to be in his own parallel universe, unable to connect with the people around him. The metaphor is almost too perfect. The physicist who claimed that other versions of reality exist was himself unable to be present in the one reality his children could access. The man who said all outcomes occur was unreachable to the people who needed him in this particular outcome. Elizabeth Everett, Mark's sister, struggled with this absence her whole life. She was diagnosed with schizophrenia. She attempted suicide multiple times before finally succeeding in 1996. Her mental illness was severe and likely had biological components that had nothing to do with her father's distance. But the distance could not have helped. Growing up with a ghost for a father, in a house where the most brilliant mind never engaged with you, cannot have made things easier. And then there is the final detail, the one that makes the whole story almost unbearable. Elizabeth's suicide note, asking for her ashes to be thrown in the garbage so she might meet her father in another parallel universe. She understood the theory. She understood that her father had proposed the existence of other branches, other versions of reality, and in her final moments, she reached for that theory as a source of hope. Maybe death was not the end. Maybe it was a doorway. Maybe the branches were accessible after all, if you just knew how to look. The physics says she was wrong. Decoherence separates the branches. There is no known mechanism for crossing between them. Death in one branch does not transport you to another. It just ends your existence in that branch. But the physics also says that somewhere in some branch, Elizabeth Everett is alive. The version of her that did not develop schizophrenia. The version that got help in time. The version that grew up with a father who was present and loving. That version exists. The mathematics guarantees it. Elizabeth could not reach that version. She could not become that version. She could only end the version of herself that was suffering in this branch, hoping that somehow, against all the physics, she would find her way to something better. It did not work. According to the theory, it could not work. But you can understand why she hoped, and this is perhaps the cruelest aspect of the many worlds interpretation. It tells you that better versions of reality exist, that the people you have lost are alive somewhere, that the suffering you have endured did not happen in every branch. It shows you the possibility of paradise. And then it tells you that you can never reach it. The branches are sealed. Decoherence has done its work. The interference between branches has been destroyed by interaction with the environment. What was once a unified wave function has split into components that can never reunite. The other yous are out there, living their lives, but they might as well be in a different universe entirely. Which, in a sense, they are. Some people find this comforting. They like to think that somewhere, somehow, the people they have lost still exist. That there is a branch where their loved one did not get sick, did not have the accident, did not make the choice that ended everything. The existence of those branches, even if unreachable, provides a kind of solace, but others find it torturous, knowing that a better version of your life exists, that a version of you is living it right now, and that you can never access it, or even confirm it exists. Knowing that your suffering was not necessary, that there is a branch where it did not happen, but that you are stuck in the branch where it did. This is not comfort. This is a new kind of hell. A hell where paradise exists, but you are locked out forever. The physics does not tell you which reaction is right. The physics does not tell you how to feel about the branches you cannot reach. It just tells you they are there, sealed away by decoherence, real but inaccessible. And so you are left to make your own peace with it, to find your own way of living in a branching universe. To decide for yourself whether the existence of better branches is a comfort or a curse. The physicists who accept many worlds have made their peace. They go on with their research, they raise their families, they live their lives as if this branch is the one that matters. Maybe it is. Maybe the only branch that matters to you is the one you are in. Or maybe there is no mattering at all. Maybe the concept of mattering does not survive the transition to a many worlds universe. Maybe in a reality where everything happens, nothing matters in the way we thought it did. These are not physics questions, they are questions about meaning, about value, about how to be a person in a universe that may not care about persons. Physics tells you what exists. It does not tell you what to value. The many worlds interpretation has a conclusion about you that nobody was supposed to find. I have tried to tell you what that conclusion is. I have tried to explain what the physics actually says, what the implications actually are, what it means for your existence as a person if this theory is correct. I do not know if it is correct. Nobody knows. The surveys show no consensus. The debates continue. The measurement problem remains unsolved, regardless of which interpretation you prefer. We are 100 years into quantum mechanics, and we still do not understand what it means. But if many worlds is correct, then everything I have told you is true. You are branching right now. Copies of you are being created as you watch this. Some of those copies will have good lives. Others will suffer horribly. All of them are real. All of them are you in every sense that matters, and none of them can reach each other. That is the conclusion. That is what nobody was supposed to find. That is what the mathematics says about you, about your identity, about your future, about your place in a reality that branches forever in all directions. Now you know. In some branch, this knowledge destroys you. In some branch, it sets you free. In some branch, you close this video and never think about it again. In some branch, you cannot stop thinking about it for the rest of your life. All of those branches are real. All of those yous exist. And the you who is watching right now, the you in this particular branch, will never know what happens in the others. You will only know what happens here, in this branch, in this life, the one where Hugh Everett died at 51. The one where Elizabeth Everett killed herself, hoping to find him. The one where the theory that explains quantum mechanics might also explain why your existence is infinitely more complicated than you ever imagined. The branching continues. It never stops. It has been happening since the beginning of the universe, and it will happen until the end. You are part of it whether you accept it or not. And somewhere, in some branch, there is a version of you who has found a way to make peace with all of this. A version who understands what many worlds means and has figured out how to live with the knowledge. A version who can face the infinite without despair. Maybe that version is in this branch. Maybe it is you. Or maybe it is in another branch entirely. One you can never reach. One that exists only in the mathematics. Real, but forever inaccessible. The theory does not tell you how to feel about this. The equations do not contain instructions for how to live. Physics tells you what is true, it does not tell you what to do with the truth. That part is up to you, whichever you, in whichever branch, is still listening.